Hello everybody, and welcome to the continuation of page 3 in the workbook. What we're about to do here is to give formal definitions of the three matrix operations that we talked about in the previous video. Okay, so let's start with definition 1.0.2 here. So they're starting us off with two matrices A and B, both of which have size m by n, and any scalar c. When you see the word scalar in this course, think of that as just either a real or a complex number. It's a constant that we can multiply things by. Okay, and in this definition, we'd like to define formally what we mean by addition and scalar multiplication of a matrix by a scalar. Okay, so start with addition, A plus B. Okay, and our definition is going to be a entry by entry definition. Okay, so we're going to tell the reader how to get the entry in the ith row and the jth column of A plus B. And to do that, we'll do exactly what we did above. We'll first take the entry in the ith row and the jth column of A and add it to the entry in the ith row and the jth column of B. Okay, if we do that for every entry in our matrix, we get the matrix sum. Okay, and similarly, if we want to know what an arbitrary entry in the matrix CA looks like, okay, one that's in the ith row and the jth column, we just take the entry in A that's in the ith row and the jth column and multiply by C. And if we do that for every entry in our matrix, we get the scalar multiplication of, or the matrix A multiplied by the scalar C. Okay, and let's see, next definition, 1.0.3. Okay, here we're going to define what we mean by the transpose of a matrix. So if we start with an m by n matrix A, then A transpose is going to be an n by m matrix, okay, because we're reversing the rows and the columns. And in particular, the entry in the ith row and the jth column of A transpose is just going to be the entry in A that's in the jth row and the ith column. We noticed the same property above, okay, when we were doing the previous video. Okay, so these are the two definitions that we're going to use, and the rest of the section, or a lot of the rest of the section anyway, is going to focus on writing rigorous proofs of some properties about matrices. It turns out that this way of defining these operations makes it easier to write general proofs.